Okay, so first of all, hello everyone, whoever I've not been able to meet today in person, thanks to COVID. Um, and first of all, thank you to the organizers for letting me share this work. I am Boris Kalita, a second year PhD student in France, CSACLE, and this work could not have been possible without the collaboration of Mike Rich from UCLA, and obviously my supervisor, Emmanuel Dadi, who is part of the same institute. So what I'll be talking about today is my attempt at understanding how massive galaxies have evolved over time. And the basic idea is how do the local elliptical galaxies that are present at mainly at the center of clusters formed. And we have a general idea of how extremely star-forming galaxies evolved over time. But what I'm interested in is the uncertainty involved in explaining the initial part of the evolution. And this part of the evolution ends at about 3 billion years after the Big Bang, or about redshift 2, where observers have found a lot of compact quiescent galaxies, galaxies which are no longer forming stars. And they are very morphologically different from the dusty star-forming galaxies that one expects at higher redshifts. And so the evolution that has happened over time to give these compact quiescent galaxies is the question. Now, to kind of say that question again, I'm using this slide where one expects, if left undisturbed, a galaxy growing over time, especially at high redshifts, would be secularly evolving, which means that there is accretion of gas from the surrounding cosmological environment, where you have gas feeding the galaxy, and that leads to the formation of stars. There is some part of that gas gets expelled as outflows, and a fraction of that in turn gets recycled back and adds to the star formation of the galaxy. And all of these processes are in a sort of equilibrium. Now, from there, we have to go to the massive compact quiescent galaxy, which are morphologically very different from these gaseous disks at higher redshifts. And in order to explain this is what stood out in scientists' mind. And there are two main competing theories. One is that the accretion leads to disk instabilities within the galaxy, which ends up not allowing for a formation of a proper disk, and rather the gas collapses into the core, forming a stellar bulge, which is the main component of the massive compact quiescent galaxies. The other theory would be mergers, where gas-rich galaxies collide with each other, and because of the dynamics of this process, the gas falls into the center, again forming the massive stellar bulge at the center, and hence forming the compact quiescent galaxies. To disentangle this is a bit complicated, and one could expect that you could simply observe the accretion-driven galaxy evolution happening in action, and see whether it fits to the theory that simulators are predicting in this compaction phase that I mentioned first. However, it's a little easier said than done, because even though a lot of simulation work has gone into explaining how gas accretion leads to formation and evolution of galaxies, to actually observe that in action is a bit difficult, because based on our understanding of how accretion streams behave, one would expect that them to be present in this parameter space that I show, where it gets easier to observe them at high redshifts. However, with high redshift, you have problems of sensitivity, and hence it's extremely hard to detect. And one could go to lower redshifts, but at lower redshifts, the hot intergalactic medium in dense environments do not really allow for the survival of these accretion streams. It is not the case all the time, because sometimes you find an object in a Goldilocks zone. And that is exactly what my supervisor and his team of collaborators found and have recently published, which is they use KCWI observations of the Lyman alpha transition, which I think Patty in the first presentation already described why it's very useful to observe intergalactic gas. And they observed this. What they actually observed was a Lyman alpha halo, which is centered over 12 sigma over density of radio sources, and they termed it as a protocluster. And the streams, the Lyman alpha halo seem to be tracing streams of gas falling into the potential well of this galaxy group. And it's not surprising to be finding such detection of gas streams, especially because the structure, given its mass and redshift, fit perfectly in our understanding of where cold gas accretion streams can be observed. Now we have this object where you have accretion streams falling in, and it's the obvious next step is to understand what it is doing to the star-forming galaxies. And the star-forming galaxies are 3, and this is what I've been working on, and we've actually completed the work, and I think I'll be submitting it within the next couple of weeks or so. And what we have observed is using HST and ALMA deep ALMA observations, we find that in the 3 main sub-millimeter galaxies, the star-forming galaxies, we have massive stellar disks, which are over 10 to the power 11 solar masses. And especially one of them, Galaxy B, has a radius of 7 to 8 kiloparsecs effective radius, which places it at the highest extreme point of what is expected from a mass size relationship at these redshifts. But on top of that, we have extremely compact, like a factor of 7 to 8 more compact ALMA cores. And by ALMA core, I mean cores that are observed in sub-millimeter emission, which traces extremely dense star-forming regions. So what it means is that you have a massive stellar disk, and you have, however, in the whole galaxy, the star formation rate, more than 90% of it is actually concentrated at the very core. On top of that, the orientation of the disks fit perfectly with the galaxy, gas streams that I mentioned in the previous slide, which sort of fits in the whole regime of gas accretion coming in and feeding the galaxies and the disks themselves. And this is one of the first times we get to observe for sure that accretion is affecting the evolution of galaxies. And we have compared to simulations, and we find a lot of similarity between what are the predictions of simulations and what we observe. However, given that there is a compact ALMA core, we inevitably compare it to the formation of the compact stellar cores that I was mentioning a few slides ago. And in the scenario where accretion leads to the formation of compact quiescent galaxies, our observations do not fit, because in those simulations, a stellar disk should not have formed to such a mass, and hence we suggest that there's likely more work needed to be done in terms of understanding how this process really happens. And a key aspect of this picture, however, is yet to be completed, which we expect from confirmed MOSFER observations of about 1.5 hours that we'll be getting in January 2022. And using that, we'll try to understand the stellar dynamics to study the disk stability and hence add to our understanding of these galaxies. And furthermore, we'll also have independent tracers of star formation. Now this is what we saw from the star-forming galaxies. However, we also saw an extremely massive, extremely massive being 10 to the power 11 again, quiescent galaxy within the same environment based on its photometric redshift, which adds another perspective to this whole picture of how accretion feeds galaxies, because this would be sort of the limit to what accretion can do to galaxies. Because we have a quiescent object which has formed its stars, but even if it is in the presence of gas, in the presence of a lot of gas, it's not enough to restart star formation. And this could also add to an understanding of an early imprint of an age-environment relation, which simply means that galaxies in a dense environment can be expected to be older compared to galaxies in less dense environment. And this is something we published recently in APJ Letters. However, there's also a small addition to be done from the MOSFER observations that I just mentioned, where we'll be getting hopefully getting spectroscopic information as well as independent traces of the age of this galaxy. And finally, to make this picture even more interesting, the ALMA observations that we had after removing the contribution from the star-forming galaxies, we see that there's a little more emission, which we attribute to dust and in the surrounding medium of the galaxies, which means that there should be some reason why the dust is there, and most likely it is because of intergalactic stellar population or tidally stripped materials from the galaxies, which have direct consequences to the understanding of the evolution of the galaxies. And with that, I'd like to conclude my presentation about our first attempts at directly observing what accretion does to galaxies through direct observations of a galaxy group at redshift 3. Thank you so much, and I'm open for questions.
All right, let's.
I see.
Okay, I can repeat local questions.
Yeah, I'm having a tough time actually opening the chat for some reason.
Oh, can you? Is there a chat that you can see?
Okay. Should I read the question on the chat, or
yeah, go ahead. Yeah, you read it. Go ahead. That'd be great.
Okay, so what is the size of the massive quiescent galaxy that you found? And by size, do you mean, okay, so physically, it is quite compact. It's about 1.4 kiloparsecs, similar to the objects that we are seeing in ALMA. So interestingly, it fits a scenario where the galaxies that we're observing as star forming, if the compact ALMA core would end up becoming a quiescent galaxy, it would look something like Galaxy D. But if you talk about in terms of mass, it's 10 to the power 11 solar masses.
Okay. Is there any other questions in the chat? No?
No, not that I can
Any other questions in person? No? Okay. Well, let's thank Boris again.